All right. Welcome, you four. Glad to have you in here. Yeah, Grace is not here, so I'm not going to bring up that one. But I do want to start with a question from the the 4-4 assignment. I'm sorry, 4-5. Student asked, actually from the other section, asked me a question, but he asked it of me after the broadcast was begun and I didn't get it. Anyway, he asked me about number 41. Here's number 41 from the previous assignment. Find the limit. Limit as t approaches 0, and we've got this 8t to the negative 1 minus arctangent t. So 8t to the negative 1, of course, means 8 over t. And we all know that when t approaches infinity, 8 over t is going to approach 0. How about that second part, though? The limit of the arctangent of t as t approaches infinity. So, hard to think of these in reverse, but when is the tangent infinitely large? And the answer is when you're approaching 90 degrees, you're in the first quadrant and you're going closer to 90, tangent is getting huge. And in fact, it approaches infinity. So what's the limit of the arctangent as t approaches? So in what angle is it? It's approaching pi over 2 or 90 degrees. So since it's minus pi over 2. And the limit would end up as negative pi over 2. Now, those of you in attendance, what do you have any questions from your infinite limits lesson on 4.5? Welcome, Devin. Thanks for showing yourself briefly, Devin. That was very nice. Yeah, I know. You guys, I see everybody looking at their notes. I don't blame you. It's been a few days since we've had class. So 4.5 limits as x approaches infinity and limits as x approaches negative infinity. Oh, we might come back to that later. Thank you for looking. So here's our lesson for today. It's lesson 4.6, summary of curve sketching. So here we have another one of those lessons where actually I have nothing new for you today. We are going to gather up skills that we have acquired throughout the entire semester, and I would say 8, 9, maybe even 10 of them, and we're going to put them together to help us graph strange new functions. That's the idea here. So nothing new. Welcome, Taylor. Nothing new, but we're going to be putting together all these skills in order to like I said, graph new strange things. I call them strange because this is the kind of graph that you just never studied in algebra, and they have these little nuances. And we've developed all these really cool tools that will help us do this. But before we do that, I want to share with you a bit of humor. That's right, math humor. So here we go. I spotted this the other day, and I just had to share it with you. Did you know that in Kentucky, math is illegal? This was actually on Lexington, Kentucky TV 5 years ago. 5 arrested in math lab bust. Wow. So just so you know, you guys are all in danger of being busted. No, anyway, the director who allowed this spelling error was so embarrassed she asked not to be identified, so I won't. All right, so anyway, a summary of curve sketching. Here are some of those tools that we have already learned this year that we're going to be referring to today. You see that we had, let me make that a little bit bigger. So we had x-intercepts and y-intercepts way back in the first section of the semester. Symmetry, first section. Domain and range in chapter 1 also. In chapter 2, we started studying continuity and what breaks up a graph. Vertical asymptotes, 2.5. Then chapter 3, differentiability. Remember, in particular, a couple things you can't differentiate. Of course, the function has to be continuous, and you can't have, what, a cusp? Things like that. Then, in chapter 4, we learned about relative extrema and how those arrive, setting the first derivative equal to 0. Just recently, we learned about concavity. Second derivative, right? Positive second derivative tells us concave up. Negative second derivative tells us concave down. Also, in that same lesson, points of inflection occur when? Well, when the second derivative is 0, when you have a point of inflection. So if you get a second derivative equal to 0, it might mean you have a point of inflection. And then in the section we just completed, horizontal asymptotes and infinite limits at infinity. So we're going to kind of put those all in a big pot and make use of them as clues to come up with what the graph of something looks like. That's the goal today. So let's take our first example here. Example 1 from the textbook. It's up there on the top. 2 times the quantity x squared minus 9 over the quantity x squared minus 4. That's the function. And not surprisingly, you see in the solution right away they've dug into the first and the second derivatives because we know those will tell us key things about the graph. Let's take a look at those derivatives first. And by the way, you're going to see that both first and second derivatives are almost always expressed by the book as a factored quantity, something in parentheses as a factor. You'll see that more in the next example. But yeah. So anyway, now the derivatives, I know you don't see how they got them, so let's quickly go through the derivative. So we've got what, a quotient rule and a little bit of a product rule there. So let's get started on the I guess let's use red, a little bit easier. So the denominator times the derivative of the numerator, and the numerator is what? Actually a product rule. So the first times the derivative of the second minus the second times the derivative of the first. Well, the second is 2x, the derivative of the first is 0, so I don't need that. So denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. So what's going on with that numerator? Well, as you can see, that all cancels down to 20x. Let's just quickly do it. This is basically 4x, and 4x times x squared minus 4 is 4. x squared minus 16. Then over here we have negative 4x multiplied by x squared minus 9. That's negative 4x squared negative plus 36x. And you see what happens? 4x squared minus 4x squared goes away. Negative 16x, that should be, plus 36x is where. So anyway, obviously, so I did all of that just to show you where that derivative came from. Okay. So now, the second derivative, I'm not going to go through that right now, but we'd have to use the quotient rule again. All right. Now, let me get rid of that red mark. All right. So, when can the first derivative be equal to 0? Look at that first derivative there. 20x over x squared minus 4 quantity squared. Only when the top is 0, right? Because it's a fraction. And when will the top be 0? When x is 0. So, what's our critical number? See it down there? Whoops, hit the wrong tool. It's right here. Critical number, x equals 0. All right. When will the second? Oh, wait a minute. When will the first derivative be undefined? Now you look to the denominator. When will that be undefined? When you have a 0 down there, and that will occur when x is 2 or negative 2. So you see how that gives us these two numbers. Okay, so those are critical also. Now, when will the second derivative be equal to 0? Well, the answer is, it would only happen when x squared is equal to what? Negative 4/3. And you can't get an x squared, so that's not going to happen on top. But on the bottom, the second derivative, so you know what we just found out is there are no points of inflection because you'll never get the second derivative d equal to 0. But when will the second derivative be undefined? Again, 2 and negative 2. Okay. How about x-intercepts? How do you find x-intercepts? Somebody speak up, please. X-intercepts?
X-intercepts is when the numerator is equal to 0.
The numerator of?
The original equation.
Okay, because it's when y is equal to 0, correct?
Yeah.
Yeah, so x-intercepts have, something comma 0. So when the numerator is 0, and when will the numerator be 0? Just follow through on that, Sam.
Since it's x squared minus 9, it would be 3 and negative 3.
Yep, that's exactly correct. And here you can see they've listed those the same way you did, Sam. That's correct. And how about a y-intercept? Somebody else speak up, please. How do you find y-intercepts? When a point crosses the y-axis, what is true of its coordinates? Doesn't it have to be 0 comma something? Yeah, x has to be 0. So if you set x equal to 0 up here, what happens? You get 2 times negative 9, which is negative 18. And on the bottom, you get negative 4. And negative 18 over negative 4 is positive 9 over 2. Yep, there's the y-intercept. Okay. How can I test for symmetry? You remember how to do that? Especially symmetry with respect to the y-axis? You pick a value for x, go back to the original function up here in the corner, up on top, and you plug in any number, like, for example, 1. You calculate your answer, Then you plug in the same number with the opposite sign. And if you get exactly the same answer, that might be y-axis symmetry. Now you got to try several others, like try 2, then try -2, try 3, and then try -3. And if all three of those come up with the same answer, oh, that tells you you've got y-axis symmetry. And sure enough, we do in this case. See that down there on the bottom with symmetry with respect to the y-axis. Okay, so now what the book does, you don't necessarily have to do this, but they made up all the key things here. We've got our, our critical points were, our critical number was 0, so that's this line in the middle here. Whoops, gotta get my pen there. That's this line. Okay, then we know we have vertical asymptotes at -2 and 2. By the way, why do we? Yeah, because that would give us 0 in the denominator. So -2 and +2. So we got our key intervals set up, and then they go ahead and analyze it through all the different phases. Okay. So when you put that all together, here we go. You can see what were our x-intercepts again? -3, 0, and 3, 0. There they are right in those positions. You see how we have y-axis symmetry? Nice fold line along the y-axis. Let's check concavity. Okay, remember, we have no point of inflection. What's the concavity between -infinity and this first the first asymptote at x equals -2? Well, you see that they plug that in right here on the top, and it's always negative. So that tells me this branch is concave down. And then when you do the part from 2 to infinity, it's always positive. I'm sorry, it's always negative again, and that's this one. And when you do it between -2 and +2, you get positive concave. Oh yeah, and here's our y-intercept at 9/2, 0, 9/2, 0, 4.5. You put all the pieces together, and you pretty much now, yeah. And then as a last step, so these problems can get rather lengthy. That's why I'm only giving you 4 for next time, 4 for tomorrow. Okay, but when you're all done, check it on your graphic calculator or check it on Desmos and see how you did. Oh, you can look in the book too, but I would encourage you to use the technology to check it. Okay, let's look at a second one. Anybody have any question on that one? So these there's a lot to do. First derivative, second derivative, all these tests, vertical asymptotes, the y and x intercepts, critical numbers. Do we have any points of inflection? Do we have, all of that, there's a lot to check there. But all of those tell you something important about the graph. All right, let's go to this one. Another rational function. This time we have x squared minus 2x plus 4 over x minus 2. Okay, so when you take a derivative here, let's just take a look at the derivative, the first derivative. So again, we have denominator times derivative of numerator minus numerator times derivative of denominator. Well, that's a 1 all over denominator squared. Yeah, and on top, what happens? 2x times x is 2x squared. Negative 2x, negative 4x. And on the right, we have subtract that whole quantity. So what's 2x squared minus 1x squared? X squared. What's negative 6x minus a negative 2x? Negative 4x. So there's your numerator. You see they factored it. again. They wrote it as x times the quantity x minus 4. That factorization, why do they do that? Because you can look at it and you can tell me what would make that numerator 0. And you can see right away it's 4. Oh, okay. And what would make the denominator 0 and therefore undefined? 2. So do you see how we found these two just by doing that? Oh, and I forgot. What else would make the numerator 0 besides 4? Just look. 0, right? Because it's, I'm sorry, is it too small? So you look at that, the first derivative right up here. If x is 4, that's going to make the top turn out to 0. If x is 0, it will too. So do you see where this one? So now we can see we also have a critical number. Okay, so writing those first and second derivatives as much as you possibly can in factored form will save you time and make it really efficient to find critical values and so forth. Okay, the second derivative, everything's done. Oh yeah, let's talk. I haven't said this much, but what about end behavior? What does that mean? It means what happens as x approaches infinity. So when you get way to the right side of the graph, what's the graph doing? So let's quick do that. Look up at the function up at the top. Tell me, what's the limit of that as x approaches infinity? This is fresh because we just had this in the previous assignment. Well, the numerator has a power of 2. Denominator has a power of 1. Numerator obviously wins, which tells me it must approach infinity. So what is that? Except it's a limit as x approaches negative infinity. No, so we just did this one. Yeah. Now what happens as x approaches negative infinity? Well, again, the numerator is 2. The numerator, the denominator has a degree of 1. 2 is greater than 1. The numerator wins. But what happens on the top when you square negative infinity? You get a positive huge number. And on the bottom, what happens with x? That's a negative. A positive divided by a negative is a negative. So what these two things tell me is when you're way over on the left of the graph, you're going to be way down. And this one here says when you're way over on the right of the graph, you're going to be way right. Let's take a peek at the graph, see what I mean. So do you see when we're way to the left of this graph? Sure enough, we're way down far left. That's the limit as x approaches negative infinity. We're going to be way down here. As x approaches positive infinity, what happens? Oh yeah, we're going to be way up here. So even those limits tell you important things about the graph. Okay, do we have any, let's see, what's our critical numbers? 0 and 4. Okay, so at 0, you can see what? We're going to reach a relative max down here at the top of this bottom curve. And at 4, you see how we're going to reach a relative min at the bottom of that other branch? Yep, so that's what the critical values told us. Do we have a vertical asymptote at x equals 2? Yep. By the way, do we have symmetry here? Anybody? Do we have symmetry here? We don't have y.
I think so.
Well, there is, I guess there's a form of symmetry, but I mean, if I drew in the line x equals 2, we don't have y-axis symmetry. We don't have x-axis symmetry. You're right. There is a kind of symmetry, but none of the kind that...
Oh, right, because it's not reflected directly over the x or y-axis.
That's right. But you're right. There is a type of symmetry. That's important that you notice that, but not not y-axis, not x-axis, so we can't make use of that. Comments or questions on this problem? We're going to look at one more example. Okay, this is example 5 in the book. I'll try to make it big enough for you guys. By the way, I'm trying to make it big enough so you can see it. Sketching the graph of, so this is, notice this one looks less complicated. Why? What makes this a less complicated problem? I know it's a lot of terms. X to the 4th minus 12x cubed plus 48 squared minus 64x. But you notice there's no denominator? That means if we don't have a denominator, then what don't we have right away? We don't have any vertical asymptotes. Yeah, okay. So easy derivatives, except again, look at how they wrote their derivatives. They're right here. They put them in this format where they're factored. That's awesome because, well, yeah, because what? Then you can immediately, just by opening your eyes, you can see what are the critical numbers for the first derivative. You can see they're 1 and 4. And what are the possible points of inflection? Look at the second derivative. They're what? 2 and 4? So again, let's just go through this derivative. Notice the book did something really important. Did you notice how there's an x in every term of that original function? So they factored it out. So when you take an x out of that, you get x cubed minus 12x squared plus 48x minus 64. And then what you probably haven't figured out is that would be a job to factor because you'd have to try all kinds of techniques. Turns out, here's how the factorization goes. Well, no, I'm sorry. That now you got to take the derivative. Excuse me. Now you got to take the derivative. Anyway, how would you do the derivative of this? Well, you could do the product rule. The first times the derivative of the second, plus the second times, 1, and then do your best at factoring it. If you can get it factored, you can save yourself a lot of time. Okay. So, what about x-intercepts? Well, when will y equal 0? And you can see one immediately. Just look at what I factored up here. When x is 0, that'll cause the whole thing to be 0, right? 0 times that big mess. The other one, that's going to look, So you'd have to work on it to find that out. By the way, did you know there's a way of finding what will equal 0? Did you know that you can use, what is it called, the remainder theorem? This is an algebra topic now, and we haven't talked about it this year. But so if you want to find out what f of 4 is, all you have to do is plug it in to the original function. Okay? So I can plug it in right here. What's in this factored part? That would be 4 cubed minus 12 times 4 squared plus 48 times 4 minus 64. You do all of that work. If the answer comes out to 0, then that tells you that if x is, because 4 worked out to be 0, that tells you that 4 is a y-intercept. I don't know if you remember that, but anyway. All right, so now we know the x-intercepts. How about y-intercepts? Well, if x is, okay, let me think. If x is 0, since there's an x in every one of the 4 terms, that's going to make the whole thing 0. So we've got that taken care of. No vertical asymptotes because we don't have a denominator. What's the limit of this as x approaches infinity? Got to be infinity, right? Because x to the 4th power is going to rule. What's the limit as x approaches negative infinity? Well, when you take a negative times itself 4 times, it's again going to be a positive. So that's going to be positive infinity. So in other words, it's going to start high on the left, and it's going to end high on the right. So this does not have any horizontal asymptotes. Here, take a peek. Yeah, I'll show you this in Desmos. This is what the graph looks like, and that even though the graph looks like it's vertical, you can see that top is forever moving to the left. And so it starts high and it ends high. Okay. Now, critical numbers 1 and 4. Look at the graph. 1, that's the low point, and 4, sure enough, that's what? A point of inflection. A point of inflection where it's changing from concave down to concave up. Yep. So anyway, how can I find, yeah. So we pretty much So there's all these techniques we want you to use. That's why I've only given you 4 problems for tomorrow. You don't necessarily have to do all of them. As you can see, this one didn't have any symmetry, so they didn't even list it. Just like the last one didn't have any symmetry either. So they didn't even list it in their list of features. But you want to list as many as you possibly can. Okay. So the assignment, as you can see, is just 4 problems. 5, 11, 19, 65. You know, I'll be honest, the problems that you're going to do on this section are probably not good candidates for a test the way they are, because they ask you to do like 5, 6, 8 things. However, I could make the question more specific and say, are there any points of inflection in this? And then all you'd have to do, you'd go right at the second derivative and test. In other words, instead of testing all the things, I could send you to do, one of them. Is there symmetry in the following equation? But still, these are good problems, and you take out all of your tools that we've learned from the beginning of the semester to now to kind of do detective work on each of these, and then make your best guess at a graph, and then go check it on your graphing calculator or on Desmos. Any questions? Anything you want to go through? Devin, you got knocked out there, I see. Did you have anything you'd like to ask about? Any of you? Okay, well, thanks for attending, and I am looking forward to being with you tomorrow.